So the other time, good afternoon, everyone. The other time we were looking at probability in hydrology. I want to see. Yes, I think we finished. So today we will be looking at hydrologic design criteria. And first I want to look at whether we have notes for that. And then for the environmental ecology, about ecology, its theory, I'll just send the notes and you can look at them yourselves. So it's only 10 pages. So first I need to check, I want to check whether I sent the notes. probability, lumped flow, hydrology. Yes, everything. I think you have everything for that I intend to teach for this course. So we have learned in engineering hydrology 1 about hydrology. We learned about the occurrence of water, in very many types or in very many forms, vapor, and also, well, sometimes solid water, but mostly, especially in the tropics, we focus on water. So what is the main importance of this water and this kind of understanding? Why is it necessary to understand the occurrence of water? One, we know many hydrologic structures many structures in hydrology, water is an enemy. For example, I saw a comment recently. Someone is saying, that was on Twitter, someone was saying the enemy of roads is number 1, water, number 2, water, and number 3, water. So, but also again, when you look at the scenario we are in at the moment, we have very little water to use in our, in our farms, for example, and what have you. So again, this water, and for example, in Nairobi, if this drought continues, you may find that some estates start encountering water stress. And, we know it is through civil works where we design water supply systems. So water is a very important aspect in the engineered world. In this particular session, we will be looking at the impact. We will be looking at the impact of hydrologic events on a water resource system, and we will be able to choose values for key variables of the system so that it will perform adequately. For instance, we want to choose the right value of discharge of a stream across a bridge so that the bridge will perform adequately. We want to choose a capacity of a reservoir that will be able to accommodate or to carry projected flows enough for a certain water supply system, or whether it is irrigation, drinking water, and what have you. So the those variables, the values that we select are what we call the design criteria. And here we have plural because normally when we are designing, we do not only use one criteria. For example, if you are doing an urban drainage system, you may find that you need the watershed area. That is one of the criteria. You need the design storm, and you need the, the curve number. All those are design criteria. So that is an example, just to give one. When it comes to, so hydrologic design may be used to develop plans for a new structure, for example, a dike, a bridge, whatever kind of hydrologic structure you can think about. Develop management programs for better control of existing systems. For example, by generating floodplain maps, so that you can now use that map to restrict or to zone areas that are not prone to flooding and that can be used comfortably to erect buildings. Of course, there are so many other factors, so many factors that are used in design of structures. For example, when you're doing bridge, there is the structural bit. There is the capacity of the number of roads that will pass through there. When it comes to, say, a water treatment plant, or let's say a water supply reservoir, we have very many things like, of course, you will consider the public welfare and safety. You have to consider economics, and other factors are aesthetics, legal issues, geotechnical, structural designs, and so forth and so on. And so when we are talking about these hydrologic design criteria in this aspect, we are not going to go into these other aspects of focus to us, as hydrologists, as engineering hydrologists, is to determine the flows, hydrologic flows that are going to pass through these systems. When it comes to water resources management, most structures are constructed either for water control or water use. Water control, for example, dikes, drainages, and so forth and so on. Water use, such as water supply, and so forth and so on. In the first case, when it comes to the water control, we want to prevent floods overtopping riverbanks, and therefore we construct dikes somewhere along the floodplain, like the dikes we have in the Nyando River, so that we can contain the floods within the river riparian zone. When we come to water use, we want to construct a dam that will be able to hold enough water even during the longest drought possible. And we were able to see the other time the probability or was it risk of occurrence of a drought. And of course, when we were doing that, we considered the duration of the drought. Was it like 2 years? Like now, I think we're in the third year of a drought year, of a dry year, really a drought year. So, and we are yet to see how this year is going to go. So droughts last long periods, floods last very short periods. And because of this, you realize that when it comes to design, hydrologic design criteria for water control, for water use, you may have to do an analysis of minimum flow of a period of of a long period. In order to do this kind of hydrologic design or to develop this hydrologic design criteria, we develop what we call, or rather, we have variables that are usually used. For example, you can have the hydrologic design scale, estimated limiting value, or probable maximum flood, maximum precipitation possible. And if you give me 1 minute, I receive a call. Hello? Yes. Uko hapo, okay. Thank you. Give me 1 minute or two or five. I have to get something. Now we should continue without interruption. So where are we? So I was talking about the various how to design this criteria, how to develop this criteria, and there are had said that you can use three ways: hydrologic design scale, estimated limiting value, under which under that group where you can also find maximum precipitation possible, and then we have probable maximum flood. And the hydrologic design scale is usually defined as the magnitude of the design variable within which a value must be selected to determine the inflow into the system. And we have an example of a hydrologic design criteria. For example, if you are doing minor structures, you are allowed to select a flood or a flow with a return period between 2 and 100 years. That is what we talk about hydrologic design scale. When it comes to intermediate structures, then major structures, intermediate structures, the design, the return period of the events should be between 50, let's say 50 and 70 years. And then when you have major scale, then you have structures varying from return periods of events varying from about 50, 70 years to 100 years. So that is the hydrologic design scale. And in this case, it gives approximate ranges of the design level for different types of structures as shown. Now, the question is, do I have anywhere the type of structures which, which are considered to be minor, intermediate, and major structures? And we shall see whether those definitions are there. What is an estimated limiting value? An estimated limiting value is the largest magnitude possible for a hydrologic event at a given location based on the best available hydrologic information. Normally this concept of expected limiting value is connected commonly with maximum precipitation possible, and from that maximum precipitation, of course, we have a probable maximum flood. For example, assuming we had the measurement of rainfall during Noah's time, then that one, we would use that as an estimated limiting value for whatever purpose. That is just an example. But in this case, in this case, currently what we have, for example, in Kenya, one of the oldest events that we know that had created a lot of havoc was the Uhuru floods of 1963. During the period when we were getting Uhuru, there's some major rainfall events that occurred. And I stated here again that that rainfall caused the Lake Victoria water levels to jump by 1 meter. 1 meter for such kind of a lake, it's not a joke. So when you look at the hydrologic design criteria, the estimated limiting value is occurring, at the end, at the far end of the hydrologic design scale. at the end of a design scale. And rarely, on very, very rare occasions, do we find ourselves using the estimated limiting value. Because you see, we are using a structure with a return period of a very large return period. For example, if we were to do the flood of 1963, probably you would find that that flood has a return period of over 100 years, actually. Yeah, so on very, very rare occasions and on very sensitive structures do we use this. But it is not that it is never used. It is, for example, go to places like Netherlands, where they have reclaimed the sea. Assuming we were to have an event that causes the sea levels to rise, what would happen with the reclaimed land, that is, or with the structures that constrain the water? Look at the mega structures, the mega dams that have been constructed in the world. I think the largest dam should be in China, if I'm not wrong. What would happen if that dam failed? So we still have designs of those major structures, and when we talk about major, we associated with the risk associated. A major structure is a structure which, if it failed, we would have catastrophe of an unmeasurable magnitude. Then we have what we call the probability-based limits. Because for the estimated limiting values, it is usually not easy to calculate accurately using probabilities or probability models, probability distributions. Probability distributions, it's usually very difficult to calculate estimated limiting values from probability distributions. And so it is determined through what we call deterministically. That is, you do not apply chance to determine it. You know, and we will say the largest flood was that flood of Noah, for example, and this was the magnitude. So you do not use probability at all. It is used as it is. That is what we call deterministically. You do not apply any kind of probability analysis or what have you. However, below the scale for intermediate structures, even for some of the major structures, a probability or what we call a frequency-based approach is commonly used. So you carry out probability analysis using the methods that we learned when we were doing probability statistics, develop probability distributions for your data, and then use those distributions to, to select your design criteria. Normally, for a structure with a high cost of failure, for a structure with a very high cost of failure, the ELV approach is recommended, and I think I have mentioned it before. But for other structures where the the cost of failure is not very high, then you can use the probability-based or the frequency-based approaches. And for the approaches, of course, for those two approaches, the return periods are generally lower. There are some generalized design criteria. Of course, at the end of the day, you as an engineer, what you choose to use is based solely on your, what can we say? It's based on your prerogative decision. Design is very subjective. You find that, for example, Bill Clinton here or Boris Obuya, and Boris Obuya, when designing the same thing, they can end up using totally different variables, but at the end of the day, each make a very robust design. So generalized design criteria for water control structures. For example, if you are doing dams with probable loss of life, where the hazard is very significant, you can the return period, or you can use the 50 to 100% of the expected limiting value, estimated limiting value. For large dams, like what I said, the largest dam we have in the world should be in China at the moment. You have to use the maximum, the 100% value, that is the highest, very highest measured value. Then we have, of course, from this level, we have large structures. From this level, we have large structures. So above all these structures, urban drainage, you can use 2 to 25 years return period. For highway bridges, 10 to 50 years. Of course, remember 10 to 50 years. Most of the roads are designed to last 10 to 50 years, so a return period of 10 to 50 years would be appropriate. So these are indicative, typical values. I already stated that based on the expected consequence of failure, you can classify a structure or consequence cost of failure. Structures can be classified either as major, intermediate, or minor. When we are, however, because now whole examples have been given are about flow, discharges, and what have you. What about when we are dealing with designing for water use? In this case, we are interested in periods when we have insufficient supplies. That is usually what is of concern to us. And theoretically or on record, normally droughts are fewer in historical hydrologic recorded than there are extreme floods. And it is usually very difficult to determine drought design levels through frequency analysis, especially if the design event lasts several years. For example, I remember we had a drought in the year 1984. I just hear of it. I hear people talking about the drought of 1984 where people had money, but there was no food to buy. Then I think in the beginning of the 1990s, I think there was a period, there was also some certain drought. And apart from that, the other one that I'm noticing now is this one of this year. Then before that one, there was you know, our grandmothers used to even remember periods and times based on droughts. They would say, oh, they were born just before this drought, they were born, this one was born just after this drought, you know, and so really droughts are not as common as flood events. So normally when designing, especially municipal water supplies, what is used in this case is what is called critical drought of record. And that is the worst recorded drought. Due to the limitation, the limited data, due to the limited data, when designing for municipal water supply, the hydrologist goes to the complete hydrologic record, and especially on river flow, and then selects the critical drought on record. From that complete record. And what does he select when we are talking about critical drought in record? The flows, the water flows, minimum water flows in that river during that period when there was those drought. Now, there is a catch when we do that, because now you see we are using an event in the past. The critical drought of record is, of course, a historical record, but we are designing for the future and we do not know. Now, the limitation about this and why it is a challenge to do this as opposed to when we are doing floods, because for floods we can always estimate. We can always estimate or use probabilities. We can use probability to what do we call it, extrapolate. We can use probabilities to extrapolate. Here, you are using just a single event in the past and assume that in future, the worst that can happen is what happened in the past. So the risk usually associated with basing this on a single historical event is usually unknown. And that is now the biggest challenge of this method. And to overcome this, we have methods whereby synthetic stream flows are generated using computers and random numbers to prepare synthetic flows that are statistically equivalent to the historical record. And then now these synthetic stream flow records are used, are considered to be simulations of future, and then they are used. But I can assure you, in our country, we still use critical drought of record. Because also even this synthetic stream flow records generation, this is a suggestion that was done long time in the early 80s, before even the 90s. By now we have sophisticated methods, but even then in our country, we still work with critical drought of record. I mean, we are still waiting for the West to come and work for us. Before, where are we? Selection. Before we start on the selection of the design level, I wonder whether we are going to take a break. Design storms. Yes, I'll come and select. We start on design storms. So, how do we select the design levels? how do we select level? And what is a design level to begin with? It is the magnitude of the hydrologic event to be considered for the design of a structure or a project. So are we going to select, if we go back to the previous figure, are we going to select this level for minor structures? Are we going to select that? And even then, which exact value are we going to select? And to do that, we usually apply 3 procedures. We have, for example, the empirical approach, and we have the empirical approach, we have the risk analysis, and then we have the hydroeconomic analysis. And here we are going to look at 2, the empirical and the risk analysis, because we have already done some bit related to that. One, we start with the empirical approach, and the most extreme event among past observations is usually selected as the design value in this case. And the probability then that the most extreme event of the past 10 years will be equal or exceeded during the next 10 years is estimated as, that is the probability P of the most extreme event of the past 10 years will be equal or exceeded once during the next 10 years is estimated as n, next 10 years divided by n plus n. Very simple. So, for example, the probability that the largest flood observed in n years will be equal or exceeded in the next 10 is, for example, the probability is 0.50 once you have calculated. That would mean then n and n are equal. The period when you have measured hydrological data is equal to, the future period for which you are estimating the probability. That is, for example, if we are doing with floods. However, if we are doing, and in this case, the event is instantaneous, and I want us to put the instantaneous in quotes. It is a period that takes short period. For example, a flood, a rainfall event that will take a short period. But for droughts, this event lasts a certain period. So the method of calculating probability in this case is different. And if you have a drought lasting m years over a record m years over a record of n years, the probability that the event will occur within the next 10 years is usually given by n minus m plus 1. So, and the probability that the event will occur will be n minus m. M is that period when we had the drought, then you plus 1, then divided by n plus n minus 2m plus 2. And we have a solved example there. So it is very easy. So now, how is the risk done? Now the risk, once you have done the calculated the probability, you now use the probability to calculate risk. You use the probability to calculate risk. So these things are just very straightforward to apply. So you calculate the probability, and let's say in a particular jurisdiction, let's say in our country, we assign a risk factor of of maybe 0.5. So first you have to calculate the probability, and then from the probability we calculate risk. How do we go about it? How do we go about the risk analysis? The risk of failure, R, can be calculated as 1 minus the probability, 1 minus, into bracket 1 minus the probability. You could say it is 1 minus the probability of non-exceedance. And remember when we were doing probability, the probability that an event is equal or exceeded, the probability that an event is equal or exceeded is equals to 1 over return period. So it is the same reasoning here. So you get, in this case, if you have a return period, if you have selected a return period, the whole of this is the probability of non-exceedance, because this is the probability of exceedance. So if you get 1 minus P, that is probability of non-exceedance, and then you minus 1, so that you can get the probability that the event is exceedent. And the risk now, and the risk associated will be 1 minus the probability of non-exceedance, the probability of you get the probability that of the whole of this gives the probability of exceedance. This is probability of exceedance. Once you minus from 1, you get probability of non-exceedance. And then, so if you get again 1 minus the whole of this, you get probability of exceedance. Where N is expected life of the structure. And when we talk about the life, remember, I talked about N being the design life and not the life expectancy. N is the design life and not the life expectancy. So if you were then to, or rather theoretically, we have a graph or a graphical procedure where you can easily calculate risk when you are given design life and return period. When you are given the design life N and the return period of your design, you can easily calculate your risk. So for example, if we have a design life of let's say we are doing an intermediate structure, we take 50 years, and in that design life, we select a return period of about 20. We select an event with a return period of about 20 years. You are going to have a very high risk. We are going to have very, very high risk. And we can see where we have low risks, very low risks, we can check the risks that is below 50, 0.5, for example. If a structure has a return period of 500 years, 500 years, 500 years, and we select a design life of 500 years as well. That is absurd. That is really absurd. Yeah, but when you select an event that is extreme for design, then the probability that it will even occur is usually very, very, very low, and that lowers a risk. So that I was checking something because I was looking at this line of 0.5, and I was saying if we select an event with a return period of 50 years, that will be this point. Then you would have to or rather it coincides with a design period of over a design life of over 200 and something years, and that is really quite absurd. But most of the time you find that because our design lives are very low sometimes, very low. And then, like if you're dealing with urban hydrology, some very low return periods, you end up with very high risks, associated risks, because the events occur quite often. And an example of an explanation about this risk calculation is, for instance, if you know, if an engineering hydrologist was to be 90% certain that the design capacity, and 9% certain that is 90% risk, but the design capacity of a culvert will not be exceeded during the structure's design life of 10 years. So the risk of 90 and then the design capacity of 10 years. So 90, 10 years. Then you will have to design. For the. You will have to design for the 100-year peak discharge of runoff. So essentially, that is how you read the table. Very interesting. But if a 40% risk of failure is acceptable, the return period can be reduced to 20. The return period can now be reduced to 20. 20 will be about here. And then still the design life will be still, let me do. Yeah, so let us assume that line is not correct, but it is between 0.3 and 0.4. Once you have determined these values, or you have determined your event with a certain return period for a certain design life, you have to do another thing. And of course, that one is now not hydrology, because you have to provide things like factors of safety. For example, factors of safety usually account for design uncertainty. For example, yes, you provide safe factors of safety or safety margin. For example, a freeboard. A freeboard will allow for a closed structure, will be able to help limit the buildup of pressure in a system. And other factors of safety, for example, against environmental exposure and such kind of things. But now those factors of safety are applied during maybe the geotechnical or the structural design. So here we have an example. We have an example that I have given whereby a culvert has an expected life of 10 years if the acceptable risk of at least one event exceeding the culvert capacity during the design life is 10%. What design return period should be used? What is the chance that a culvert designed for an event of this return period will not have its capacity exceeded for 50 years? And the solution is given here. So the 0.1 is the risk, So we are applying directly the equation for the risk. Then we are given n. We are given n. Yeah, so here we are given 10. 10 is the n over here, and the risk R is 0.1, and we are required to determine T. So the T is 95 years. So in the second part of the question, we So let us see whether we are going to finish. I already do not have power, and I've lost electricity. I'm using my phone's internet. Just reconnected with it. I have very low power on my computer, but let us see whether we are going to finish the remaining bit. It should not be a lot. So another design criterion that we usually consider is design storms. And we already discussed how to develop design storms. We select them from IDF curves, intensity, duration, frequency curves. But I stated that sometimes it is advisable, especially when you're dealing with flows, to use not analyze IDF curves, but develop flow duration curves. When we have design flows, and when you look at situations where we deal with design flows, one purpose of such kind of structures where we consider flows is we have flow regulation structures which smooth out peak discharges. For example, reservoirs, or we can have flow conveyance structures to safely convey the flow of downstream points where the adverse effects of flows are controlled or minimal. And when it comes to design for water use, we are concerned with development of water resources to meet human needs, to meet human demand, and also with the conservation of natural life in water environments. And the electricity is back. Let me tell you, anyone who does not have a surge protector is going to lose everything. It's going to lose their equipments. We have been having on and off electricity throughout the day. When it comes to hydrologic design for water control, however, where we are concerned with the mitigation of the adverse effects of high flows, you find that in such kind of situations, and especially if you are having a reservoir for water supply and also for flood control, you find that the hydrologic design for water use is directed at utilizing the flows, the high flows, the average flows, while at the same time the structure mitigates effects of stream the design for water use is usually directed at using average flows and at the same time mitigating the effects of extreme low flows. How does it do that? During high flows, the excess water is stored and then used during low flows. We have an example. For whatever reason, I've never understood when it comes to this hydrologic design criteria. There is usually a special focus of storm sewer design. I was muted. So we have the rational method. I don't know whether you heard what I said before. I had said for whatever reason, storm sewer design is usually given a special attention in hydrologic design criteria. I've never understood why. And normally the rational method is usually used where Q, which is peak discharge, is equals to a runoff coefficient C times design intensity or design storm times area, watershed area in hectares or in acres. So the C is a ratio of the peak discharge divided by design storm times watershed area. The question is, why do we only consider peak discharge? Why do we consider peak discharge only? Why? Because the capacity of our storm sewer has to have the capacity to carry the peak discharge. I don't know whether it is in this class I was talking about, but I didn't teach you engineering hydrology 1A. And one thing I know is most of the lecturers teaching hydrology teach the rational method erroneously as one of the method of calculating excess rainfall, and that is not true. The rational method is a method that is used in storm sewer design. The discharge that is calculated using the rational method is the peak discharge only. So you cannot use the rational method to calculate, for example, discharge or to calculate a storm hydrograph, for example. Or you cannot use it. It is limited. It is limited to storm sewer design. When it comes to calculation of excess rainfall, we have to use the runoff coefficient method and the phi index methods. Do we have another one? Yes, we can use the SES methods of abstraction, whereby you use the SES method of abstraction, and finally you have the fourth method. You can use the infiltration equations to calculate losses. So we have four methods. But the rational method is not one way to calculate excess rainfall. So when you are given this method, then the question comes in, because Q is usually the design criteria we are looking for, or the design variable, whilst the criteria we have the C, and then we also have I. So the question is, how do we determine the design storm? And I wonder whether we have that one here. Yes, how do we determine the C and how do we determine the A? Of course, determining A is the area, watershed area, and you can delineate the watershed. But the question is, how do we determine these two? One, if you remember, when we focus on the intensity design storm I, if you remember, is it you? Now I'm even confused. I don't know whether it is you or it is the other class. The maximum peak discharge is produced when the whole catchment is producing runoff at the exit, at the catchment exit. In short, the rainfall has been falling for a long period, such that water has been able to flow from the farthest point of the catchment to the catchment outlet, or rather, the rainfall has a minimum duration equal to the time of concentration. So the duration of the rainfall, Macharia had raised his hand. I don't know whether it is still needs to be, something needs to be answered. So the duration used for the determination of the design precipitation, I in the equation, is the time of concentration. Remember, we have intensity, duration, frequency curves. So you need to go to those IDFs, use your, calculate your time of concentration TC, and then use that as your duration. And remember, the durations are the K is equals to 1, K is equals to 2, K is equals to 5, K is equals to 10, whichever period, and you can interpolate within that IDF curve. Now, when we are doing storm sewer designs, are usually normally for urban areas. We usually have sub-areas and subcatchments of different surface characteristics. And I will give an example. Let's assume we are dealing with Nairobi. Go to Karen, we have pavement, but we also have a lot of trees, and we have a lot of areas with a lot of soil. Come to the city center, it's almost all pavement. Come to areas like where we, other areas whereby most of the areas are, concrete. So applying the rational method becomes a challenge, but there is a way to go about it, dividing the area into subcatchments. And for each subcatchment, of course, the design intensity is constant, but the runoff coefficient is different, the area is different, and you can just calculate Q for each, and finally sum those values together. The rational method is, however, applicable under two assumptions. One, the computed peak rate of runoff at the outlet point is a function of the average rainfall rate during the time of concentration. Remember, during the time of concentration, and during this period, the whole catchment must be contributing to runoff. Two, the time of concentration employed is the time for the runoff to become established and flow from the most remote part of the drainage area to the inflow point of the sewer, And then finally, the rainfall intensity is constant throughout the storm duration, or rather it is constant throughout the time of concentration. So how do we determine then the runoff coefficient C? Normally, runoff coefficients used with rational methods, we have some values that have been proposed. I'm guessing these are values proposed for the United States, where the runoff coefficients are dependent on the character of surface. For example, is it developed? Is it undeveloped? Is it cultivated? Is it a good condition where we have grass cover and what have you? So with these characteristics, is it forested? Is it woodlands and so forth? So with that, you can easily be able to select a runoff coefficient from this. And there is one challenge here. And again, remember I said, when designing, at the end of the day, two designs may not be, may end up being totally different, but still meet the design requirements. For example, I may come and classify an area as undeveloped and with pasture or a range with an average slope of 2 to 7%, and then another colleague would come and select and say it is steep over 7%. Both of you will end up being right, because the choice of how you interpret the field data is quite very subjective. So this runoff coefficients, you notice, is dependent on the land cover, the slope or topography, and condition of the soil. Of course, other factors that will affect runoff coefficient will be probably like rainfall intensity, proximity to water table, and you will see that why, because proximity to water table means that the grounds will come saturated faster, and a lot more surface runoff will be generated. So again, what about the rainfall intensity? And I really have talked about it. I've really talked about it. It is the rainfall intensity falling over the rainfall. The rainfall has to have a constant intensity, and it has to fall for a period equal to the time of concentration. And it is selected based on the design rainfall duration and the return period. The rainfall duration is the time of concentration of the drainage area under consideration, and the return period is usually established by design standards of a particular jurisdiction. So for example, what is the return period we want to use in our country for roads? What is the return period when we are doing flood control structures? So the time of concentration, because I've explained most of this time of concentration bit, so a little bit to explain about how to calculate the total time of concentration. It's usually the time of overland flow plus the time of, let me check, do you notice the storm drainage system, and then, so it is the storm drainage system flow, and then the time of flow from the farthest point. And let me see whether I have an example here to explain that. Yeah, so for example, if you have this outlet at C or at D, and you want to determine the time of concentration, you have to consider, one, the water flows from this catchment, and before it gets to the drainage. So that will be the TF. That will be the TF, and then from the TF, the water flows through the storm drain all the way to D. So you have to do that for all the subcatchments. So you are going to have as many as there are subcatchments. So you are going to have some other possible time of concentration. So that is another one. Then you, of course, for the subcatchments 4 and 5, and then 6 and 7, that is going to be very, very short than the rest. So we will consider maybe the subcatchment 3. Then from subcatchment 3, the water flows through EB and out. So you have to now assess the 3 of them. Which one, which of the 3 provides the longest route, and the longest route will be the time of concentration. But it's not that simple. You have to do hydraulics, use Manning's equation to be able to determine the time taken for the water to flow, I don't know whether I have an example of that. Probably not. That would be very bad if I don't. Let me check. Let us look at this example. So at the end of the day, the TF, this TF, will be given by TF is the flow through. What is the T? Is the upstream sewer connected to the outlet point, and then what is T naught? T naught. Yeah, the T naught. The T naught here is the time water flows from the catchment to the first collection point. That is the T naught, and then TF is the time to flow through the sewer lines. So T naught, water is flowing as overland flow or from whatever catchment, and then TF is the water is flowing through pipes. So let us look at an example. And TF, for TF, you have to sum. A number of pipes. For example, the water first will, in this case, if we take the subcatchment number 1, the water will flow through points A and B, then B, C, and then D, C, D. Remember, in order to be economical, the sizes vary. The sizes of this pipes will vary, and that is why you have to consider each separately. You have to calculate TF separately. And still the whatever is not there. There is an interesting, I don't know whether it is here or where it is, an interesting calculation of the how, an example I don't know whether I've given it in the tutorials or whatever, and that would be very unfair. Anyway, in case we encounter it, we are going to solve the problem. In case it is in the tutorials, we'll solve it from there. So now we go to determining the drainage area. Remember, in the rational equation, we have CIA. So we have dealt with the C, we have dealt with the I. Now we are dealing with the A. And at this point, allow me to take a poll so that we can know who is in. So for the drainage area, of course, you can do that by mapping, not really an hydrologic aspect. It's more of a survey and what have you, and that is why we have done survey sometime in our course. Those who are not there, you can see your names on the WhatsApp group. So let us continue. Who is this? In attendance with Elisha Higgins, this is who? Tevin Brandon. Okay. We continue with the drainage area. And I think that there is not much to talk about it. But the area, remember, in that equation, area is in acres. Yeah, and there is an example to provide a size, a diameter of a pipe, of a certain pipe somewhere. Of course, first you determine Q, and then from Q you calculate diameter. So you can go through that example. So finally, design for water use. So we looked at design for storm sewers. So what about design for water use? And the main variables are location, height of the dam, elevation and capacity of the spillway, and capacity and mode of operation of the discharge works. So what part really is the hydrologic is determined by hydrologic analysis, the storage capacity of the reservoir. Of course, that storage is closely related to the height of the dam, and also the location, because the location determines the catchment area, and the catchment area determines the yield. The farm yield, or the mean annual rate of release of water through the dam, that can be guaranteed, or we usually call that the safe yield. And finally, as we finish, the storage capacity of the farm yield are interconnected. Where the higher the storage capacity, the greater the farm yield, and the farm yield can never be greater than the mean annual inflow rate to the reservoir. Let us look at the overall design process of a reservoir. You do future projections of water demand, determine location and elevation of the dam, and calculate surface area and storage capacity. For present and future conditions, you compute the farm yield of the reservoir for present and future conditions. And then finally, you compare water demand and farm yield of the reservoir. So when it comes to the reservoir, it's only the sizing where we apply most of the hydrologic analysis. So we come to the end. We are not going to look at ecological flows and what have you. Maybe I just mentioned them, but we have 40 minutes. I can see whether I can just mention them in passing. It's theory. You can go look at it yourselves. It's actually a very new science, that ecohydrology. It is a new science that has been, introduced recently. And like during our times, my time in school, we did not have ecohydrology, but from promotions, from emerging technologies, that is where we have it was introduced. And recently, most of curriculum are including ecohydrology. So you can look at the definitions yourselves, then look at the need, why we need environmental flows. Look at surfaces, ecosystem services, and the interrelationships to human well-being. Why we need flows, and other key concepts of hydrology and other principles. And that's it. And I just want to mention it in passing, but it is still examinable, and there are questions that in the tutorial set, but let me mention them just briefly. Ecohydrology is a science that studies interaction of ecology and hydrology. What what is ecology? And when you look at hydrology, then you can say the ecohydrology is some sort of aquatic ecology because it is an interaction of ecology and water and hydrology. So what do we find in aquatic ecologies? We find wetlands, we find in those wetlands we find fauna and what? The other thing, the other F, the two Fs and fauna, whatever, that one. So we find crops and animals, aquatic plants, aquatic animals. Sometimes, let me check the word. Yes, flora and fauna. So the flora should be the plants and the fauna should be so you find such kind of aquatic plants and animals. So the reason why at this point we are talking about ecology is because you see we have talked about so many control structures. For example, you may find yourself doing a spillway, doing a dam, and we have fish growing in that ecosystem. Well, it is important to understand that we need to provide a pathway for fish, for example, to travel up and downstream, for instance. That's one. Two, we may need water to flow in the downstream of a reservoir in order to sustain benthic microorganisms. So those are the organisms that crawl on riverbeds. They provide life in the riverbeds. They make the riverbed to be aerated and water view. We may need to provide water for downstream riparian users. Sometimes floods, for example, floods in the Kano Plains used to sustain the Nyando wetland, but if now we construct dikes, what happens to the wetland? Where is it going to get the water? And sometimes you find flora and fauna which are endemic to a particular wetland. So this is all about ecohydrology. So later, when you look at, when you will be reading these notes, you'll find that ecosystem services, they are important because they sustain ecosystems, and these ecosystems, in the other hand, provide services to humans. And in addition to providing those services, they also sustain endangered species, they sustain endemic flora and fauna and so forth and so on. So basically this principle of ecohydrology, it's basically about that. And for us, I just wanted us to have the introduction. If you do your master's, you may learn aquatic ecology in totality, whereby you study the ecology, for example, of a river system from the head, from the river source to the river mouth. And there you look at the characteristics of the microorganisms and, the expected geological characteristics and such kind of things along the river from the source to the mouth. And this is something you can learn yourselves. In case you have any question, you can always ask. Otherwise, we are finished. Normally, Engineering Hydrology 1B is one of the shortest courses. So we are done with the course, not unless we have questions. From next week, of course, we have our cut next. When do we have our cut? Let me check it. If you people wrote, when do we have our cut? I need to post these things. On 22nd, that is next week. From 3. So when do we have our revision? Because how do we have a cut without a tutorial? That is tricky, isn't it? We cannot have a cut without revision. But we already did it. We did some of this stream flow routing, and I needed to I needed to give a clarification of this deconvolution equation. Sijaikalia bado. I normally have to sit. I've not had time to sit down and remember and try to remember some of these things, how I was doing it before. So what do you think, class? We have 27th. The exam is on 14th. It is 22nd. That is next week. Can we have physical class on 22nd so that on 1st we can have the cut? So that on 22nd, we do revisions, we do tutorials, mu revise pia, come with questions so that we can ask specific questions as we prepare for the cut. Then you remember another thing, the exam will be near. Sasa hapa nimeona watu wameongea. Ai, kumbe huwa mnaongea. So we have so many people. So I can change it to fast because it would be unfair to you people if we did the cut when we have not done tutorials. So let us do the cut on 1st of March. I will give an assignment because we are only going to tackle stream flow hydrographs and flow routing. I need to give an assignment for the remaining part to be submitted during the exam. Okay. Any question before we break? Today I usually have back-to-back courses classes, so hata kwa yangu imekauka. Any question? Any question? Mi nangoja muni release muniambie no question. We will only, Mercy, we are only going to have one cut and one assignment. Nganga umeamua kunimalizia. We are only going to have one assignment. No question. Thank you, Tevin. So Tevin has released me on behalf of the class. Thank you very much. So you have a nice evening. And on Wednesday, when we are coming to the class, remember, I'm not going to lead us through any question. You are going to lead me. You are going to come up with the questions for us to solve. So have a good evening.